Hello, am I audible? Just like react with a thumbs up or anything if I'm audible. Okay. Uh, yeah, so I'll start the session now. Just 1 second. Are you guys able to see my screen? Okay. So let's start with the session, the third session of the critical learner space, which is radiation mechanisms. So basically, in this session, we will be covering about radiation, its types, and the various fields related to radiation, such as photometry and spectroscopy, and their various applications. So let's start with talking about what radiation is. So, radiation is one of the primary messengers of information in the universe. And an important thing about radiation is that it helps us learn more about the sources, such as celestial bodies, stars, planets, and all that emitted. Uh, okay, could you unmute if unless you have a doubt? Okay, yeah. So yeah, as I was saying, that it helps us learn more about the sources that emitted these radiations, such as their temperature, shape, composition, velocities, and whatnot. You can know a lot about the celestial body just from the radiation it is emitting. And these electromagnetic radiations or EM waves are basically composed of orthogonally oscillating electric and magnetic fields. So you can see here that this picture shows that there's one electric field oscillating along the y direction here, and then there is one magnetic field oscillating along the z direction here, and they're both orthogonal, and these two oscillating fields create an EM wave which propagates in the x direction here. And you can even find the direction of propagation of the wave by finding the cross product between the electric field vector and the magnetic field vector at any given point in time. The entire array of electromagnetic waves comprises the electromagnetic spectrum. All right. So uh, the EM spectrum that we study, the different types of EM waves, they have been divided into groups depending on their wavelengths or frequencies, and they have been given names. So if you see here, in the decreasing order of wavelength, you can see that we start with radio, which has waves of the order of 10 raised to 3 wavelength, 10 raised to 3 meters of wavelength. Then we go to microwaves. Then we go to infrared waves. Then we go to visible light. Then we go to ultraviolet rays. Then we go to X rays and then gamma rays. And so the EM waves have been divided into these groups so that we can study them more efficiently. And they all have different properties. And there's another feature of these waves that this part shows. The temperature of the objects at which this radiation is the most intense wavelength emitted. Okay, so this basically the thing is ki when you try to study the spectrum of some source, then the radiation at which the most wait Is my screen visible now? I think my screen was not visible for some people. You can see my presentations and all, right? Okay, cool. Okay, so I'll continue. We're not covered much. We were still on the second slide. That the EM spectrum has been divided into different. Wait, is it still not visible? Uh, for anyone, is it not visible or anything?
Yes,
It's visible for you or not visible?
it's not visible.
Wait, I'm really sorry about this. Yeah, now is it visible? Now can you see the presentation and all?
Yes.
Cool. Okay, so I'll continue now. So yeah, so we were talking about the different types of EM waves that depend on their wavelengths, and we have talked about the different uh, EM waves here: radio, microwave, infrared, visible light, ultraviolet rays, X-rays, and gamma rays. And there's another interesting property that we will talk about in the upcoming slides, is that the temperature of the objects at which this radiation is the most intense wavelength emitted. So when you try to study the spectrum of any source, then there's a particular wavelength for which you'll receive the maximum intensity rays, and that also depends on temperature. So as you increase the temperature of that source, the maximum intensity waves will come from the smaller wavelength EM waves. So wait, okay. So yeah, so you can see here that as we decrease the wavelength, as we increase the temperature here, the most intense wavelength, most intense waves will be coming from smaller wavelengths, and this comes from Wien's law, which we will talk about in the upcoming slides. So let's talk about another property of the atmosphere, which is its ability to allow radiation to pass through it. This property is called transmissivity, and this transmissivity varies with the wavelength or the type of the radiation. The gases that comprise our atmosphere absorb radiation in certain wavelengths while allowing radiation with differing wavelengths to pass through. And the areas of the EM spectrum that are absorbed by the atmospheric gases are known as absorption bands. So you can see here that the atmosphere has like a value of transmissivity associated with it, and it depends with the kind of waves that you're considering. So like if you consider radio waves, then it basically lets radio waves completely pass through it. So, and if you consider stuff like gamma rays, X-rays, and ultraviolet light, then the atmosphere does not let those rays pass through it. So, and that's an important thing in letting us know that usually when we talk about radio telescopes, those are located on Earth on the ground, because we can study them without any issues, because the radio waves can pass through the atmosphere. But if you're, let's say, establishing like X-ray telescopes and all, then we have to have them in space, because there'll be no such barriers from the atmosphere and all. So let's talk about black body radiation now. And black body radiation is an example of thermal radiations, where basically the mechanism in which these radiations are emitted actually depends on the temperature of the source. And what a black body is a body which absorbs all the radiation incident on it and reflects nothing, and basically transmits no light coming on it. So whatever light is falling on the black body it completely absorbs it. So that's a black body, and we'll be studying about how like black body emission works, black body radiation works. So uh, in the start, the black body radiation was people were trying to approximate how to calculate the black body radiation. And the first way to do it was the Rayleigh-Jeans law, which was an approximation to black body radiation through classical arguments. But once it was done, there was a problem that was arising up when this approximation was done, which is known as the ultraviolet catastrophe. Basically, it was that when you calculate this value for, let's say, lower wavelengths or higher frequencies, then you will see that it'll start going to infinity, as given by this black graph. This is the graph predicted by the Rayleigh-Jeans law, and that turns out to be a problem, because you can't have the intensity of radiation going to infinity. That's not possible. So that was a big problem in the Rayleigh-Jeans law. So next, what turned up was the Wien's law, which was the next approximation to explain black body radiation. What this did was that it accurately described it for higher frequencies or short wavelengths. This law was derived from thermodynamic arguments and using the Maxwell-Boltzmann distribution for atoms, as you all might have heard. And this is how this approximation is written. There's an exponential term here. So you can see that, if the frequencies start increasing, or the wavelengths start decreasing, then it won't tend to infinity anymore, and it will tend to a finite value instead. But after that, there was another development in the calculation of intensity, where Max Planck derived the formula for black body radiation using the newly developed quantum theory, which states that energy can be quantized in terms of the emitted flux per unit frequency interval per unit steradian, where steradian is a unit of the solid angle. The Planck function is given by this. So this was an improvement over the Wien's law, where Max Planck used the quantum theory to derive an even better formula for calculating the black body radiation. So before we continue, do you guys have any doubts? Any doubts regarding anything I've discussed right now? You can raise your hand if you have a doubt. Yeah, Adrita, yeah.
Can you please explain the part of the ultraviolet catastrophe once again, please?
Yeah, sure. Um, yeah, so basically here you can see that the first approximation that came up was this. So this was the calculation that was made by the Rayleigh-Jeans law. And you can see here that if you decrease lambda here, lambda is the wavelength, and if you try to decrease lambda, it will just try to increase, and the more you decrease it, it'll keep increasing and start tending to infinity, which theoretically is not possible. You can't have infinite flux, infinite intensity or anything. So that turns out to be a problem, because this formula is predicting something that's not possible. So that was called the ultraviolet catastrophe, and the reason it was called ultraviolet is because for lower lambdas, like you're going towards ultraviolet rays and all. So yeah, you got it.
Yes, thanks.
We're on WhatsApp. Someone is asking what exactly BV is. Uh, okay, lambda is the wavelength, and this is nu. Nu is the frequency. This is basically the intensity of the radiation. Intensity is like a measure of like what the brightness of the source is. And it's basically written in two ways, like either written in terms of wavelength or written in terms of frequency, right? So this is like the intensity of the radiation. Um, and it's just basically a measure of like what the actual brightness of the source is. So like you can compare the brightness of two sources using this method. All right. Okay. And this is for a particular like frequency and all. Any other doubts? Okay. So I'll move on. Another thing you can do with black body radiation is that, as you can see in this graph, so basically, let's say that you're trying to study the spectrum of any star and all, and you get, let's say, a particular value of intensity or brightness with associated with a particular frequency. All right, like some frequency of light is giving this much intensity. So you can basically find out the value of the temperature of the source just using that. Because if you see here that, let's say you try to plot from a particular source the intensity versus frequency values um, of the radiation coming from a source, then you'll get a graph like this. So like this is for 10 raised to 6 kelvins, you get a graph like this. All right. If you try to decrease the temperature, then the graph will start shifting and also going downwards like this, right? And as you keep decreasing it, it will keep shifting and going downwards. And as a consequence of this, you can only get one value of temperature for a particular value of intensity and frequency. Like if you, let's say you get this point. Oh wait, my mistake. Let's say you get this point, then then you can easily say that the temperature of that source will be around 10 raised to 4 Kelvin. So in this way, the graph of the black body radiation also helps us in calculating the temperature of the source emitting this radiation. All right. And another application of the thing I mentioned in the previous slide was that the universe's cosmic microwave background, which fills the entire sky. And I will talk about the cosmic microwave background in the upcoming slides. This is a great example of a situation where temperature can be inferred from a single frequency observation. So the cosmic microwave background is basically this, these EM waves and this light that is like pervading throughout the entire space. And it's been there since the Big Bang. And we can use the frequency versus intensity values for this to calculate like the temperature of like different parts of space and all. And let's say if we try to do that, the value of the temperature we get is about 2.7 kelvins. So that's another application of this method. Like you use the cosmic microwave background to calculate the temperature to be about 2.7 kelvins. Now, once, let's say we have studied all of this and we get the intensity values, we can find the flux emitted by black body. The flux is basically the amount of light reaching us per unit time and all, right? So because the values that we were studying earlier was for a particular frequency or for particular wavelength, like all the formulas were for that. But if we want to find the total flux, the total amount of light reaching us like per unit area and all, then we can find the flux emitted by the black body, which is given by the Stefan-Boltzmann law, which is equal to this, where this is the Stefan-Boltzmann constant, and this depends on the fourth power of the temperature of the source. All right. And there's another law associated with black body radiation, which is the formula to calculate the frequency at which the highest amount of intensity or brightness is observed from a source. So like, as you could see from this graph, that there is a peak value here. So what is this value? This value is given by this formula. This is called the Wien's displacement law, where new peak or peak frequency is directly proportional to the temperature of the source. So if you start decreasing the temperature, the peak frequency will also decrease. And so let's move on to talking about the cosmic microwave background. So the cosmic microwave background is basically this light that is basically present in the entire space. And the thing was that after the Big Bang, it took about 300,000 years for the universe to cool down to a temperature at which atoms could form. And that temperature was about 3000 degrees Celsius. After that, matter became neutral and then light could travel freely. Basically, the universe became transparent. And this first light that came after matter became neutral, that first light is called the cosmic microwave background, right? So basically, since the time that that radiation was released, the universe has expanded and becoming at the same time cooler and cooler. And because it's becoming cooler, the peak frequency is decreasing because the temperature is decreasing, or the peak wavelength is increasing of that of those radiations. So similarly, the cosmic background has also been affected by the same process. It has expanded and cooled down. And today we observe it in the microwave spectrum. So today you're observing the cosmic microwave background to be mostly in the microwave spectrum, right? And um, and again, as we had discussed earlier, once we had fit this to a black body curve, we found that the temperature of the cosmic microwave background was 2.725 kelvins currently. And this was also used as evidence to find out that the universe has been expanding and cooling for about 13.7 billion years. So this was a major like use of radiation. Like we could find out the age of the universe just by studying the cosmic microwave background, right? Now, there's another way that there's a way that we study these spectrums coming from source stars and all. So we use photometric filters to study these sources. So what photometric filters do is they filter out pass bands, and what pass bands are these specific wavelength ranges in which astronomers observe celestial objects. So like let's say you have a wavelength range around like the visible light blue color, like a small range of let's say a few nanometers and all. Or the ultraviolet, right? So basically what photometric filters will do is they will take these small passband or wavelength ranges and only let those ranges pass through them, filtering out everything else, right? So you can see there's an example of some examples of photometric filters here. Like you can filter ultraviolet light, R can let a red pass through. So these help us study specific wavelengths in an easier way. So now if we use this, then we can basically check different filters and check the intensity uh, of the radiations passing through these filters for different filters. And let's say we find that if a star appears brighter in the ultraviolet passband compared to the infrared passband, then it's likely a hot star emitting more ultraviolet radiation, and vice versa, again due to the Wien's displacement law. And you can see that this is here a graph of, let's say, using different filters. So let's say if we use the filter filtering blue or something, then you can see that it will be transparent for wavelengths around the blue region, but it won't let any other wavelength pass through it. Okay. And again, before we continue, does anyone have any doubts? Just raise your hand if you have a doubt. Okay, so I'll continue. Now let's talk about the field of photometry. So photometry is the science of measuring the amount of light received from a star. And the word basically comes from two Greek words, photo meaning light and metron, which means measure. And that's basically what photometry is. You're measuring the amount of light that you're receiving from a star. That's all. So the main thing that photometry does is measure the flux of a star. And the flux is the same thing, that the amount of light coming, the total amount of light coming to us per unit area, right? So this is and the units of flux are given here. This is watts per square meter. So this is the amount of energy from the star that has reached us, and photometry is what tries to study it. And there are two terms related to photometry that you must all know, which are absolute magnitude and apparent magnitude. So let's tackle them one by one. Let's start with apparent magnitude first. Apparent magnitude is basically a scale that helps us find out how bright a star is when it's at its actual distance from Earth. So like it's basically a measure of telling how bright that star appears to us, right? That's why it's called apparent magnitude. And this scale is basically backwards and logarithmic. Basically that if let's say a star is has a higher apparent magnitude, then it will be fainter. In that way, it's backwards, right? So larger magnitudes correspond to fainter stars, and brightness is another way to say the flux of light in watts per square meter coming towards us. Okay. And so you can see here, this is a few examples where you can see that the sun has an apparent magnitude around here in the negative regions, and then the moon and Venus. So you can see that the ones that which appear brighter to us are have a lower apparent magnitude, and the ones which are like very faint have like really high apparent magnitudes. So in that way, this is a backward scale, and there's a way to relate different apparent magnitudes using this formula, which is like this is one apparent magnitude and this is the other one, and you can relate to them by their actual fluxes minus 2.5 log b2 by b1. So let's say you have a brightness or flux ratio of 100, for example, then you'll get an apparent magnitude difference of 5, right? So you can use this logarithmic scale to basically express the apparent brightness or the flux that you're receiving from any particular source, right? Let's move on to absolute magnitude. Absolute magnitude is the apparent magnitude the star would have if it were placed at a distance of 10 parsecs from the Earth. So what we do is you take the apparent magnitude and you basically take a reference, like let's say 10 parsecs, and you take all the sources that you're considering and basically shift them to 10 parsecs. And then doing this will either make it brighter or fainter depending on whether it was closer or further from 10 parsecs. And this basically helps us compare their actual brightness values, because currently what apparent magnitude does is their fluxes or their brightness values that you're receiving depend on the distance that they are from us as well, because if the further it is, the fainter it will appear for you. But if you put them all at 10 parsecs distance from the Earth, then um, you can compare their brightness values in a fairer way. So you can basically you can use the inverse square law of Wright and find the ratio of brightness at 10 parsecs to its brightness at its known distance d with this relation, and then you can find the formula for the absolute magnitude in this way by plugging these values into the previous formula. So you can basically take its apparent magnitude, and with this and the distance that it is from us, you can find its absolute magnitude. And then you can use absolute magnitude to compare brightness values, like their actual brightness values that they're emitting. So you can see here that if our sun was at 10 parsecs from us, its magnitude would be 4.8. So that's its absolute magnitude, but its apparent magnitude is minus 26 because it's much closer to us compared to 10 parsecs. So yeah, let's continue. Let's talk about spectroscopy now. Spectroscopy basically studies about spectrums, and spectrum basically is a full range of frequencies emitted by a particular source, and we study the various spectra emitted from these sources to find out more about them using techniques under spectroscopy. So basically, we use many techniques to study about these spectrums that are coming from a source. And there are three kinds of spectra that come from the source, which are continuous spectra, emission spectra, and absorption spectra. So let's talk about them one by one. First is the continuous spectra. Basically, when a radiation source emits at all frequencies over a range without breaks, the spectrum is called a continuous spectrum. So if you're basically receiving a spectrum of light from a particular source, then if you're receiving a range of frequencies from a source, then basically you will be receiving all of those frequencies without any breaks. So that spectrum is called a continuous spectrum. A classic example of such a source is called an incandescent lamp or something. So you can see that this is a plot of a continuous spectrum. Like there is no breaks at all. You're receiving all of them, although at different fluxes and all, but you're still receiving all of them without any breaks. Then comes emission spectrum. Basically, when there are radiating objects that emit radiation only at some specific frequencies or wavelengths, then the spectrum contains a set of discrete bright lines. So like, let's say you have atoms that have different energy states, and they basically, you have electrons that drop from higher energy states to lower energy states. Then that loss of energy can be released as a photon, which we see as emission lines. So you can see that we see some discrete emission lines coming from a particular source. So this is called an emission spectrum. And then there is an absorption spectrum, which is when a radiation that passes through a particular cool gas. So what can happen is that some of the photons can be absorbed by it to excite the electrons in the different energy states of the gas, right? So if let's say some radiation is passing through and there's a gas in front of it, so that gas can absorb some of the radiation to excite its own electrons to different energy states, and then you won't be able to see those photons in your whatever device you're using to study the spectrum. And these lines are called absorption lines. So you can see here that some of these lines, which are called dark lines, you're not able to see because they have been absorbed by this cool gas, right? So this is the third type of spectrum, which is the absorption spectrum. So here's an interesting video on absorption lines I would like to show you guys. You can see. So you can see here that absorption lines are being formed because of that sodium there, right? So as you guys saw in that video, that that sodium was basically absorbing the light passing through it, and it was creating a dark line. And that's a good example of how absorption lines are created. I'll leave the link in the slides as well. The slides will be shared later. So yeah, before we continue, any doubts? Any doubts, you can raise your hand and ask. Okay, so no doubts, I'll continue. Yeah, so let's continue by talking about the Doppler effect. So it's a very interesting phenomenon that happens with light and with waves in general, which is when a light emitting source starts, let's say, moving towards or away from the observer. Then what happens is that the light it emits, its frequency starts appearing to be shifted, right? So let's say that the source is moving away from us. Then what will happen is that the radiation wavelength we observe will be longer with respect to what the actual wavelength is. So this radiation is said to be redshifted. Whereas if let's say the source is moving towards us, then the wavelength of the radiation that we observe is shorter with respect to what the actual wavelength which was radiated, right? So this radiation is called blue shifted, right? And there's a formula to calculate the redshift. So let's say you have a source that's moving away from us, receding from us at a velocity v, where v is the recessional velocity. Then you can calculate the redshift in the wavelength using this formula, right? And then you can basically find out the new wavelength using this formula. And another application of Doppler shift is how we use it to measure the distance to star. So basically Hubble, who basically made the Hubble's law, he discovered that galaxies are not only moving away from us, but their velocity of recession is directly proportional to their distance from us. And this is due to the expansion of the universe, that as the universe starts expanding, everything is moving away from each other. So the galaxies are also moving away from us. And we can find out their velocity of the recession and actually actually find it to be proportional to their distance from us. And this proportionality is written like this, where h naught is the Hubble's constant. So we can basically, using, let's say, the redshift, find the recessional velocity. And using that, we can find the distance to the stars that we are trying to study. So this is an interesting application of Doppler shift. One aspect of spectrums and stuff I would like to talk about is intrinsic broadening. Basically, it's a type of spectral broadening of these spectral lines. What happens is when, let's say, theoretically, you would measure the line to be the graph of the line to be somewhat like this. Let's say it emits a photon and you get a line like this, right? But what happens is that generally these spectrums are broadened, that you will basically receive a broader spectrum of radiations with as compared to what you would calculate theoretically. And this happens due to a variety of reasons. So one reason is intrinsic broadening, and this comes from quantum mechanics. Now you don't need to worry too much about like how it comes and all if you don't know, but it comes from Heisenberg's uncertainty principle, which is basically that if you're using the uncertainties in energy and time, then you can basically say that their product will be greater than equal to h by 4 pi, where h is the Planck's constant. And since the lifetime of these excited atomic states is finite, let's say electron is going from an excited atomic state to the ground state, then that lifetime of the excited atomic state will be delta t, which will obviously be finite, so it won't be zero. So delta E will also be not zero. And therefore, there's an uncertainty in the energy and also the frequency value of the photon that's emitted. So due to this uncertainty, you won't just receive like one particular value of wavelength or something. You'll receive like a very a broad range of frequencies because of this uncertainty that's coming up. And this uncertainty creates this spectral broadening of lines. And this broadening is basically Gaussian in nature. So Gaussians are basically like these curves, like you can see. Like, so this is the nature of the broadening that you will see, right? And basically, one way we can use intrinsic broadening is, first of all, let's talk about the 21 centimeter line. So basically, this is a spectral line that we study, and it helps scientists know a lot about molecular clouds and all. So basically, the large star forming molecular clouds in space are very cold, and they do not have any spectral lines in shorter wavelength regions of EM spectrum, such as visible, right? So what scientists do is that they rely on the 21 centimeter line to detect such molecular clouds and also use the Doppler shift to find their velocities. So what happens in the 21 centimeter line is that, let's talk about the hydrogen atom's ground state. Ground state. So there are two ways where the ground state of the hydrogen atom can exist. One where the spins are aligned, and one where the spins are anti-aligned, where the spins are in opposite directions, right? So this spin comes from quantum mechanics and all, where like, the electrons and protons have like a spin value associated with them. And there are two ways in which these ground states can exist. And there's a 50% chance of each being formed. Now, the one where they're aligned is at a higher energy, and it can quantum tunnel down to the lower energy, which is the anti-aligned state, and release a photon of wavelength 21 centimeters. So it's losing energy and releasing a photon of 21 centimeters. An interesting fact about the 21 centimeter line that now we'll start referencing the intrinsic broadening is that it's the narrowest spectral line in the universe, because the intrinsic broadening in this line is very less, because the lifetime of this aligned state, the higher energy state, is very high. So delta T is also like really high. So what happens is delta E will tend to go down, and in a lot of cases delta E will tend to go down, and this will greatly reduce the uncertainty and hence the broadening in the spectral line. So if you'd like try to plot the bright intensity versus wavelength values again, when you try to study the 21 centimeter line, you will observe it to be a very narrow line, and it's in fact the narrowest spectral line in the universe. And another application of 21 centimeter line was that it helped scientists discover dark matter, when scientists studying this line found that the stars revolving along the outer edges of the galaxies, they were found to revolve about the center much faster than expected. So you can see that radiation has helped scientists discover so much, such as the age of the universe and dark matter and whatnot. So it has great impacts. Another example of a widely used radiation line is spectral line is the H-alpha line. The H-alpha line is the first line in the Balmer series of the hydrogen atom spectra. So the Balmer series is when any electron drops from a higher energy state to the first excited state, as you can see here. And H-alpha is when it drops from the second to the first excited state. And it is a very prominent line in the optical region. And it is one of the easiest ways for astronomers to trace out the hydrogen content of gas clouds in the universe. You can study the amount of H-alpha you're receiving, and you can find out how much hydrogen there is in gas clouds in the universe. Another example of spectral lines is the Fraunhofer lines. The Fraunhofer lines are a set of spectral absorption lines. These are dark lines because that's what absorption lines are, seen in the optical spectrum of the sun. In the visible light region of the sun, you can see dark lines when you try to study it. And these are formed when atoms in the solar atmosphere absorb light being emitted by the solar photosphere. Solar photosphere, like, and basically the light coming from the solar photosphere is absorbed by the atmosphere, and you can see dark lines in the visible region. And one interesting thing was that the video that we saw previously on the sodium absorption lines, that is a demonstration of how the sodium dark line is created. So you can see here that in the Fraunhofer lines, there's a line created by the sodium as well in the solar atmosphere. And that video previously was in kind of simulation on how those Fraunhofer lines are created and how they appear to us, right? So yeah, again, before I continue, any doubts? Yeah, Yuvraj. Yuvraj, I'm not able to hear you. You're not audible. Wait. Try messaging on WhatsApp your doubt. Or on the chat. Wait, I'll check. Okay. Yeah, okay. The 21 centimeter line. Okay, I'll discuss about that. Just 1 second. Yeah, okay. I hope you can see my screen. 21 centimeter line. This. Yeah. So basically, wait, what doubt did you have?
So I wanted to know like exactly how did those 21 centimeter lines form?
Yeah, okay. Okay. So, okay. The hydrogen atom in its ground state basically has two possible ways it can exist. So each, let's say the electron and the proton has like a spin value associated with it. So this comes from quantum mechanics, that like all the particles have a spin value. And there are two ways in which this ground state can exist, where let's say the spin of the electron and the spin of the proton are aligned. One where the spin of the electron and the spin of the proton are anti-aligned, where like they're in opposite directions. And this state has a higher energy with respect to this state, the one where they're anti-aligned. And when, let's say, the one with the aligned state transitions to the anti-aligned state, it will lose energy, and this energy manifests itself as a photon of a wavelength of 21 centimeters. So you got it?
Yeah, but and on this 21 centimeter line, do we see objects in the space that emit these lines specifically?
What? I'm not able to hear you clearly. What?
Let me tell.
Okay. Yeah. So, wait. Yeah, so you're asking like what kind of objects we see, right? So basically we see, let's say like you have like, as I've discussed here, uh, like large star forming molecular clouds, like in space, let's say you have clouds of molecules and they're really cold. So you can't really observe like their spectral lines in shorter wavelength regions, like visible. So like it's easier to observe those in that. Um, so uh, what happens is because they have hydrogen content as well, they emit a lot of 21 centimeter lines, and we use these lines in these coming from these molecular clouds and all to detect, like, detect them and all. And as I discussed another example here, like when scientists were discovering like stars along the outer edges of the galaxies, there also they were using the 21 centimeter line to study them, right? So got it. um, okay, I'll move on now. Let's talk about another example where we use spectroscopy. We also use spectroscopy to detect exoplanets. So basically, the reflected light of a planet that coming from any source contains absorption bands due to minerals in the rocks present for rocky bodies, or even due to the elements and molecules present in the atmosphere. So light can pass through or reflect off these things, and some of the lines can be absorbed, which we see as absorption bands. And through this method, we have 3,500 exoplanets and their material compositions have been discovered, and we have discovered various compounds as well in these exoplanets. Okay. Another application is how we use it to detect binary stars. So there are cases when binary stars are so close together that they cannot be resolved using a telescope. So like, let's say that you're trying to observe them using a telescope, but they appear so close together that you cannot properly like differentiate between them. So what you do in this case is you use spectroscopy to detect them. And in here, we basically use the phenomenon of Doppler effect of light to detect them. So what happens is when you observe this binary star or these two stars, basically binary star is two stars revolving about their common center of mass. So they will show a composite spectrum as shown here. The spectrum of each star will be added together. This composite spectrum becomes easier to detect when these stars have a similar luminosity and of different spectral class. So spectral is basically like you divide stars and you classify stars into different groups based on the kind of spectrums they emit. So let's say they are of different spectral class, then they will emit different kinds of spectrums, and so it's easier for us to differentiate between them at all times, and also if they have similar luminosity, so that we can like compare between them in even easier way, right? And now because they're revolving around each other, about each other, we can detect their presence by detecting the periodic red shifts and blue shifts in their spectrums. So you can see here that let it go to the first one. So let's say when it starts, they're moving tangentially to each other. So you observe no Doppler shift. Then one of them is moving towards us and one of them was moving away from us. So you can see that one of the spectrums is blue shifted and one of them is red shifted. Then again, you will see no Doppler shift because they will be moving tangentially. And then the opposite will happen. The one which was blue shifted is red shifted now, and vice versa. And if we observe this kind of pattern, we can basically say that we have detected a binary star. And now, as the final topic, I would like to discuss about non-thermal radiation, which is basically where the mechanism of the radiations does not depend on the temperature of the source, but on other mechanisms. And another thing about non-thermal radiation is that here, the intensity of non-thermal radiation usually decreases with frequency. So in thermal radiation, if you increase the frequency, the intensity of the thermal radiation will increase, right? But in non-thermal, it will usually decrease. So the first type of non-thermal radiation is synchrotron radiation. In synchrotron radiation is basically the radiation emitted by a particle, to be precise, charged particle moving in a magnetic field. When such a particle enters a magnetic field, it starts moving in a circle or a spiral, effectively accelerating, and this results in the production of EM waves. Because when charged particles start accelerating, they start emitting electromagnetic waves. Under non-relativistic conditions, that is when these particle velocities are well below the speed of light, these radiations will be called cyclotron radiations, and they won't be strong enough to have much astronomical importance. So you can see here that there's a magnetic field here, and a charged particle is basically moving in a circle here. And as it's accelerating due to the centripetal acceleration, it's emitting some synchrotron radiations. Okay. Now, if the electron starts moving at relativistic speeds, then it will become significant and it will be called synchrotron radiation. And one source of synchrotron radiation are quasars, which are basically like these galactic nuclei located in galactic centers, which have a lot of emit a lot of high energy radiations, and they are one source of synchrotron radiation, not only at radio wavelengths but also at visible and X-ray wavelengths. Any doubts? Are there any doubts in the chat? Okay. All right, I'll continue. I'll continue with masers. So masers are another example of non-thermal radiation. Maser basically stands for microwave amplified stimulated emission of radiation. Now this sounds very similar to lasers because that's the same thing for light. And masers are a very interesting phenomenon that you can see in space. And what masers do is that masers are basically these molecular clouds, and basically due to a phenomenon called masing, their radiation is enormously amplified compared to what it would have been. So let's talk about that. So basically in the interstellar medium, you can sometimes like a small group of molecular species such as water, hydroxyl radicals, silicon monoxide, methanol, and many other molecular species. But what happens is because they're very scarce, they appear in small groups, their line emissions would be very difficult to detect, right? So, but there's a phenomenon called masing, which forms masers, and it helps us greatly in detecting these molecular species in space. So, in simplified terms, masing occurs when these clouds of these molecules encounter an intense radiation field, such as that from a nearby source, such as a luminous star. It can also occur when they collide with the far more abundant H2 molecules. So due to these two effects, what will happen is a lot of these molecular species will start jumping to higher excited states. And what is called a population inversion will start happening, in which there are more molecules in an excited state than in a stable ground state, right? And because there are way more molecules in an excited state, you will receive a lot more energy, a lot more radiation. So basically it's amplified. And this phenomenon is called pumping. And as the radiation causing this pumping travels through the cloud, the original ray is amplified exponentially, emerging at the same frequency and phase as the original ray, right? And these masers have been used for detecting extrasolar planets as well. Right, so extrasolar planets are basically like planets located outside the solar system, and we've used use masers to detect them as well. Say like you're seeing these radiations be greatly amplified, so you can use them to find out about extrasolar planets as well. So with that, I'm done. If anyone has any doubts, they can ask. And before I end the session, I would like to show you guys about an interesting simulation that I found online. This is a simulation of the black body spectrum. Like you can basically adjust values of temperatures here, and you can check like some intensity values, like the total intensity coming from a source. But here it's like the flux here, and you can basically adjust like you can adjust the temperature to find like what the graph of the intensity versus wavelength will be. And basically it's a very nice simulation to show how black body radiation works. So you can see that the peak wavelength is also shifting as I change the temperatures. So I'll share this with you guys, and you guys can also try it out. So yeah. So yeah, any doubts?
I guess I had a doubt.
Huh? What?
I had am I audible?
Yeah. But what did you say?
So the working principle of a maser, is it like similar to just the lasers that we study in nuclear physics?
Yeah. It's just
So it's the same, right? Just for microwaves.
yeah.
Okay.
Cool. Any other doubts? Wait, I'll just see the doubts in the group. H alpha Forest. I'm not exactly sure. Yeah, sorry, I'm not exactly sure. I'll also go through this. H alpha Forest. I don't think I'd gone through this in my presentation, but yeah, I can't like explain like properly what these are. So yeah. So if there are no more doubts, then I'll end the session. I'll share the assignment and the slides also in some time. Hope you guys enjoyed the session. And yeah, thank you a lot.